Hey everyone, welcome back. Hope you all had a restful weekend after finishing the first assignment. Well, since it's a condensed course, we have no choice but to get right back into it because the midterm's in a week. Woo! So, today we're gonna, oh no, not the projector. Hold on. There we go. So today we're going to pick up where we left off on strings.c. And actually, before we do any of the content, I'm going to just finish up writing some of the where'd the projector go again? What the heck? Am I going to have to press the USB-C button every 5 seconds? Am I even still recording? Okay. If I'm just rambling at any point and the projector's actually been off for 5 minutes, please get my attention. So yeah, strings. At the end of last week, we had a main method and I think some declarations of functions, but no definitions. So let's fix that. SSH into Aviary. CD into comp2160.
I just have a random question.
What's up?
Say kids at Killdeer, does everyone have a funny little?
Yeah, excellent.
I have one too that I don't remember right now.
Yeah, excellent question. So Aviary is made to seem like one computer when you work with it, but it's actually several. Uses a thing called round-robin DNS, the definition of which isn't important, to connect you with whatever Aviary system is available at the time. So there are several different systems in Aviary, and each of them is named after a bird. So Aviary is a word for a fancy birdhouse, and all the computers are birds, and the CS admins are hilarious. So I'm actually going to log out and log back in again, and I'll probably get a different bird. Oh, still Killdeer. So I guess both times that I logged in, this was the most available system. I think someone left this mic on, or on over the weekend or something. Anyway, let's CD again. And I believe we called it strings, or string class example. Yeah. Cool, so let's get acquainted with this again. We wrote a definition of a struct, which is kind of like a class, except it doesn't have any behavior built in. Used typedef to stop us from having to write struct string every time we wanted to use our string struct. Now we can just say string, as in these forward declarations. We wrote a main line, and just barely started these functions. So let's continue. So in this function, we're going to do exactly what I told you not to do, and I promise we'll get into actually good advice later in the lecture, but we're going to commit the crime of returning a stack-based array. And then, well, we're doing that because it's the simplest way to actually work with our new struct. And then later on, either later this lecture or in the next lecture, we're going to learn about dynamic memory allocation, which lets you allocate memory on the heap instead of the stack. And then once you know about that and all the pitfalls that come along with it, you'll be able to return arrays as you please. But for now, we're just going to throw this on the stack. This is like a constructor in a Java class, and we're just going to take the input C string and then copy it into our string. So yeah, we're just going to copy until we reach the end of string character in the input. And then, since that loop terminated and didn't do any copying when it got to the null character, and of course our string needs to have that character to denote the end of it, we're just going to slap it in at the end. Let's see. Yes. Thanks for catching that. And since our string keeps track of its own length, first of a few improvements for safety we'll make, we got to set that. I is conveniently set to the number of characters before the null byte by the time the loop terminates. And then we return it. Let's think about that. Okay, yeah. I'm just making sure for myself now. Yeah, because I++ will happen after it gets to the index of the last character, and then that +1 is the number of characters. And now we're just going to do charet, and it's going to be very simple. Just, oh yeah? Mm-hmm. Oh, that's the same mistake as was pointed out earlier. It should be input rather than string. Thanks for catching that. So for this, we're just going to do a standard array index. This is genuinely no better than just using array indexing on a C string, but now that we have this special function / method, we'll use it as a base later to add safety features. So I think this will run fine despite the stack-based arrays, because in the main line, we don't do anything. Oh, actually, printf might mess up the stack. Let's see. But it hopefully shouldn't mess up the contents of the string we made. Whether it does or not, we're going to move on, because kind of the point of the example is that it's just adding unnecessary complication to the to C's built-in string functionality, but then we're going to justify our unnecessary complication by Well, first learning about safety features in the lecture and then implementing them. So let's compile it. Cool. It works. Miraculous. So yeah, our example seems to work, and that would be good enough if we were engineers, but we're computer scientists and we're better than that. So let's figure out how to make this scale. Which brings us to our learning outcomes. So we're just continuing our discussion of interface and implementation. And we're actually going to take a look at what that means in our code. So we're going to design and use interfaces and then hide implementation details, which is helpful, borderline necessary in large programs. And this one we may or may not get to today. This is the solution to our stack-based array problem, and it has a simple interface with a few gotchas that you need to know about. Oh, I probably should have went here before I started working on the program. Oh well, we did all this. So, I was just talking about big programs and how you need to sort of approach them differently. So when you're going beyond just single file assignments for courses, this definitely all applies in the real world, but you'll even wrestle against this later on in your education. The required software engineering course is all about making one big product and maintaining it. And courses or assignments in some other courses, like distributed computing, can get really complicated. So yeah, it's complicated. So there are a few problems that come with scale, which is that the programs are difficult to understand in their entirety. Like when you just have a single file, you can easily understand the whole thing. But more realistically, at a job, there's going to be no one person who understands the entirety of the thing you're making. And also it's difficult for multiple people to work on. If one person can never understand the whole thing, then it's really difficult to collaborate, because you'll find that you sort of get out of sync in terms of the knowledge that each person has. And we sort of get around this and reduce the amount of code that we have to manage by making reusable structures and concepts. And the practice of splitting up our programs into reusable parts to make them more manageable is called modular design. So we hope to take our big, monolithic, unmanageable programs and split them up into smaller, easier to understand components, allow for multiple people to work together, and extract reusable structures and concepts. So this is sort of like some stuff that you've already used quite a bit in development: libraries. Like, do you know or have any idea of how system.out.println is implemented? What about ellipse, which you've probably used in processing, possibly? Comp 1010? Maybe out of date with that one. What about that? Think that's a Python thing? Whatever. Do you even care? Probably not. You don't have to understand exactly how println writes to a buffer in your terminal in order to use it. You just use it. And the ability for you to do so is granted by a lot of thought on the part of the developers of system.out.println or ellipse or np.linespace. No. So there are two main parts to modular design: interface and implementation. I've been saying those two words a lot recently, and we're going to finally figure out what they mean. And our main goal is to separate these two things into different parts. In the classes you've written in Java, but in previous courses, they've likely had the interface and implementation pretty close together. You managed to hide some implementation details using private variables and methods, and we're basically going to take that a bit further. So just think about it. I'll stare at my watch for 30 seconds while you think of what interface means to you, because it has a few different meanings in a few different contexts. So you might have thought of things like user interfaces, or maybe interfaces like the whatchamacallit on screen that allows to physical components in a system to interact. So in our context, interface is what two pieces of code use to interact. And in more concrete terms, it consists of the public function signatures or prototypes. So that is the parameters, the number of parameters, and the types of those parameters that they take. And we also care about the return value of those functions. Data type declarations. I'm just going to peek over here for a sec. To explain something that'll come up again later. We already have separate declarations and definitions for functions. We're going to do the same with types, and we kind of already have. This typedef statement is a declaration, and the struct and all of its components are a definition. So we're going to later separate these two so that others working on the code will only see that a structure exists and not have to worry about how it's implemented. And then once we hide the implementation details, any code that uses our structs will be unable to depend on any specific implementation details, which, as it turns out, works wonders for maintainability. As long as you maintain a consistent interface, you can change the implementation all you want, and it'll still remain stable and usable, which you can imagine is pretty important if you're the author of a code library and you want to make changes without breaking all the projects that use that library. But even if you don't end up making libraries at your job, these techniques will still be super useful just when making large projects. You could think of your own code as a library that your coworkers sort of implement in their own projects, other parts of the code. So yeah, declarations, not definitions, in our interface, like that. And I think this is a pretty good definition. Might be on a test. An interface is the minimal set of information you need to know to use this thing. So I'm going to go back to this one. We have no idea how system.out.println works. We don't even know what data type or whatever out is. We just know that it takes a string, and I'm sure there are some other details like a return value, but we barely need to know those, and if we do, they're available on Java's documentation website. So the way println actually works is unimportant. It might be changing constantly throughout development, but because those implementation details are hidden, we don't need to worry about them. So now the implementation, on the other hand, consists of function implementations, data type definitions, like the struct definition to correspond with the type def. And note that we have a type def interweaved with the struct definition here. This is a convenient way to basically take these two statements and put them into one. It's useful to do in your implementation so that the functions you write, the function implementations, can use the simpler version of the type. But in the interface, you would just have the type def. So we're going to talk about how you would take some sort of monolithic program. Say you have just some absolute mess of a program that's just one file that's thousands of lines long, probably has a bunch of functions that do a bunch of things each. So you want to make this good. So there are two concepts you should know. One is functional decomposition, which is about how you think about the system and what parts it should be made of. And then the implementation is less conceptual and more technical. It's about the code and the files. What files do you have? How should they be organized, etc. And then how do you put it back together again? We're going to be talking about multi-file compilation later in the course. Well, probably this lecture and next. And talk about build systems, which you will wrestle with in co-op work terms and real work. Detailing how each file should be compiled, how they should be linked, like the compiler thing, and just how they should be combined into a single executable. So let's talk more about functional decomposition. I'm going to be throwing around a lot of jargon. Good thing these slides are available online. So first step is to identify your data model. We'll talk more about that soon. Identify any invariants. We'll talk about that a lot soon. And identify how data is input, modified, and output. These are basically different parts to the implementation. The interface, because we want to basically turn parts of our program into things where you know how data goes in and how data goes out, but any part of the program using this doesn't need to know how input is turned into output. So what about the data model? When you're thinking about what your data model should be, and in more practical terms, the data model, it's mostly type definitions, like a common problem in object-oriented programming is dealing with parts of a program that really don't fit into the strict everything is a noun system of object-oriented programming. And that's an example of dealing with a difficult-to-define data model. So you should ask yourself, what are you being asked to represent? In our example, we're trying to represent a string, but in future assignments, you'll have to work with other data types or data structures. What data types best represent that? In our string example, that was pretty easy. You should represent a string using a string. Cool. But in other cases, such as if you're making a stack, this is assignment 2, you'll have to worry about whether you should use an array or a linked list. And more importantly, what should the interface for your thing be? In our case, our string example was a single struct relating to a string. The stack example will end up with a single struct type, a stack. But then more complicated cases, like say you're making a game and not sure how to separate different elements of levels and characters and things like that, you'll have to think a lot about how you should separate your code into types. And should I build compound data types? I guess a stack example is pretty good for this. You have a choice between, you have a choice between making your own custom struct or class to represent a stack, or you could just use an array and trust that anyone using that array will use it like a stack. That's a very bad idea. Don't do that. But in other cases, sometimes you find that what was once a struct can be represented by a single primitive type. So you should consider these situations to avoid unnecessary complication. So that was about the data model, and another very important part of this is how it's manipulated. So what kind of input do you have? For strings, it's a string. Wow, that's maybe an overly simplistic example. Wow. Well, for structs, you have, or for stacks, you have whatever thing you're storing on the stack, for example. How do I get that input? Is it from standard input, a file, some device with a custom driver, other code? And how do I transform it to or from my internal model? What kind of operations might someone else need to do? This is like going to be saying it over and over. The interface to your code is really important to make sure that other programmers working with your code are able to make sense of it. So what are the public operations, the things that are actually exposed to the outside world? And yeah, this is the interface. And then for implementation, you're wondering how you can implement just the interface and how it's used and how it's put back together again. So that was pretty fun. We just learned a bunch of programming practices. I finally told you all some stuff you should do, even if it's in pretty vague terms right now. Well, I hope you enjoyed that jaunt through some theory, because now we're just going to learn more C. Because we need to be able to, well, it's one thing to have all this theory and read over it 10 times and then be able to lecture someone on how to write good code. It's another thing to actually write good code. And we're using C for that because C is kind of crappy at helping you write safe code, and it ends up providing a good environment for learning programming practices because its lack of safety features sort of forces you to focus on good code. Of course, the lessons in this course apply to any programming language that you use. There's a thing we're going to learn about either this class or next one called design by contract, which is borderline necessary for good C programs, but it ends up, a lot of it can end up re-implementing stuff that's built into other languages, but it still sort of affects the way you think about the flow and state of your program in a way that is really helpful for debugging pretty much anything. But I'm getting ahead of myself. Let's talk in more practical terms about interface and implementation. So I'm going to use a header file. The header file will contain function prototypes, so function declarations, these things here. Struct declarations. This as necessary point is interesting because there may be types or structs that you never even expose as part of your interface. They would be completely internal, in which case you wouldn't include them in your interface header file. They would only be part of the implementation. And this part's important. You will lose marks on the assignment if your header files contain too much information. Interfaces do not expose internal implementation details. So going back to our string example, what's the public interface for strings? So what functions are part of the interface, and how much of the data type is part of the interface? Basically, you can take part of the interface and sort of replace that with exposed to other programmers. So what functions will be usable by other programmers, say, on your team at work, and how much of the data type will be exposed to them? What do they need to know to use it? Ideally, very little. And now for the practical details for implementation. Your .c files will implement the prototypes. Not sure if I've introduced this, might have, but prototypes are another word for function declarations. We're going to revisit some stuff we learned about the preprocessor to include our interface as part of the implementation. Be careful that you don't go the other way around. We absolutely do not want to include the implementation in the interface. And of course, that's where we'll put function definitions, internal implementation details, basically anything that that you need for your stuff to work, but that other programs shouldn't need to care about. And then the last part of this system is actually using the interface. So in a different .c file, you'll use that include preprocessor directive again. You'll only include the interface, not the implementation. And then you can call the functions declared in the header. So let's go back to our string example and actually put into action all this stuff I've been rambling about and separate the interface from the implementation. So we're going to create a new header file for strings, strings.h. We're going to use header guards to prevent an error called multiple inclusion, which is when if you have those include preprocessor directives in multiple files, you might end up having, well, I hope you all remember that the preprocessor is literally just text replacement. And when you use hashtag include, it straight up copy pastes the contents of those files that you include into your code. So if you include a program or a piece of code that includes another one, that includes another one, that includes another one, you might end up having a certain code file appear multiple times in that hierarchy. And that will make the compiler really mad because there are functions and structures and stuff that seem to be declared or defined twice. So we use these header guards to, well, I'll elaborate on it when we actually code the thing, but basically make sure that it's only included once. Anyway, our strings.h file will include a type declaration for string and forward declarations for the public interface. And then we're going to keep the function implementations in string.c and then move our main line into its own file. Then we'll end up with 3 files, our .c file for implementation, .h for interface, and a main function that uses it all. I keep making comparisons to working on a team in software engineering, and for good reason, because that's what a lot of you will be doing after your education. So you could imagine your app needs custom strings for some reason. You would actually make strings.c and strings.h, or equivalently, defining interface and implementation in whatever language you're using. And then in our example, main.c is sort of a stand-in for whatever other code your coworkers write, so the rest of the program. Ooh, spoilers. This is how we're going to compile it. We're going to worry about that later. For now, let's make this code slightly better. And first, I'm going to see if I remember how to split panes in Vim. I'm going to type colon for commands. And I think it's VS for vertical split. If this doesn't work, I'm just going to start a second command into Aviary and then, or a second connection into Aviary and tile these windows the old-fashioned way. But it's cool to know how to do these things on the command line. String. So this should work the same as opening creating a new file on the command line to be opened with Vim. Phew, it worked. So we're going to be taking things from our formerly monolithic string.c file and put the interface into string.h. And by the way, to swap between panes in multi-pane Vim, usually you would have to do Control W, and then one of the Vim directional keys, H, J, K, and L. H is left and L is right. So to go to the left pane, I would type H. And then to go right, Control W, L. That's kind of a pain. In the vimrc file that I uploaded to the course website, I defined a sort of shortcut. You just need to do Control H and Control L to move left and right, respectively. So let's start cutting and pasting. This is going to be more complicated than it has to be because of Vim. So I'm going to go V for visual, $ to go to the end of the line, and then D for, I think, delete, but it's actually cut. Control L to move, and then P to paste. Going to do the same thing with the function declarations. D for delete or whatever. P to paste. And there, that's our interface. String.h contains the minimal amount of stuff you need to know to use strings. And I know I said C sucks earlier in the lecture, but its system of header files separated from implementation files is actually pretty neat for this sort of thing. Makes for a more explicit separation of interface versus implementation. There's a library for game development called SDL, and I guess this could have changed in later versions, but last I used it, if you go into the downloads page, you actually just get a header, and then the actual implementations of what SDL uses. It's just in binary form so that the developers can make changes without having to break all the games made in SDL, while the header basically stays static and unchanging. It's all about making your stuff easy for others to use. And of course, in the real world /assignments, you would be very, very strongly encouraged, especially by the programming standards that you have to follow or else lose marks, sorry. Very strongly encouraged to write comments. And since your interface is the set of stuff you need to know to work with the stuff you're coding, the .h file is an excellent place to write those comments. And if you do it really nicely, your .h file basically turns into a sort of instruction manual on how to use your code. And before we move on to other files, we're going to use those header guards mentioned in the lecture. So I'm going to freestyle this. We use a preprocessor directive ifndif, if not defined, and then some sort of name or variable. Let's say strings h or string h. So basically, when the preprocessor is including this file, it'll check whether a variable called string h exists within the preprocessor. This is not actually going to end up as part of our program once the compiler is done doing its thing. So if string h is not defined, we're going to make it define string h. And we don't even need to give it a value. Just saying that it exists basically makes an entry for it in some table. And then now that we have this logic, we're going to basically make it so all this gets included in the file, or all the contents of string.h is included in the file only if this is not defined. And this is not only not defined when this is, or when the preprocessor encounters this file for the first time. So we're going to match that if and def with an end if. We just need this for just telling the preprocessor that the if statement is over. I don't know why the preprocessor uses such different syntax from regular C. Perhaps it's to help you differentiate between stuff that happens during compilation versus stuff that happens while your program is being run. But whatever it is how it is. So within this if statement, it covers the entire program. You could think of this as having an if statement really early on in your main program, seeing if some condition is true, and if it's true, running the program, if not, returning immediately. This preprocessor if makes it so everything in the .h file is only included the first time it's asked to be included. So this is how we get around that multiple inclusion possible error. So I'm going to do W to save. And then next, let's make the implementation of string. Oh wait, actually we already have string.c, so I'm going to leave string.c mostly unmodified, but take the main function and put it in its own program. Let's see if we have enough space for 3 files. If it ends up getting cramped, I'll just close the interface file. Oh yeah, that's kind of tight. So :q quits. Quits. I sort of introduced :q as a way to quit the program, but technically it's more general than that. :q quits the current buffer, which is what you call the, I don't know, you'd probably think of them more like windows. And then, of course, when you close the last buffer, it closes the entire program. So let's :q out of here as well. And then vertical split main.c. So as part of our main, we're going to include the interface that we defined. And this uses slightly different syntax from other include statements, so be careful about this in your own programs. We're going to use quotes. Basically, the difference between these quotes and angle brackets is that quotes will make the preprocessor look for a file in the same folder as the rest of the program currently being compiled, whereas those angle brackets will look for header files within wherever files for the C standard library are stored. So that might be /user/bin or something somewhere in there. You don't need to worry about that. Hey, that's another bit of interface and implementation. You don't need to know how the C standard library's header files are arranged in order to use them. So I forgot to also include string.h in our main. This is required for the linker to do its job. You need these include statements so that it's able to take the function and type declarations in the interface header and link them with the implementations in the interface, in the implementation. So let's just take main and throw it into main. Capital V for visual line, going down, 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 down. D for delete or cut. Control L to move over, and P for paste. Going to clean up some white space. Oh, and in our main function, we're going to need the inclusion of stdio to use printf, and we're also going to remove that from the string implementation. Using dd to delete a line. So yeah, we just separated one file into three, which I guess makes our singular example a bit more complicated, but it makes large programs way, way, way less complicated. You could imagine some gross monolithic program that has a whole bunch of different struct definitions and function definitions to operate on those structs, and it would get really unwieldy really fast. Now we have just a few files with clearly defined purposes, and if you're working on a small part of a large project, it's now much easier to focus on just what you need to do. So let's try and compile this stuff. So, I don't know, clang wall as usual. Main.c -o string main. Let's try it and see if it works. It's not going to work. Oh no. So when we try to just compile main, the compiler starts complaining about just stuff that isn't defined. So, for example, on line 6 of main, we declare a variable of type string, but there's no definition or even declaration of string to be found. Oh wait, there is a declaration of string to be found. It's found right here. But the definition isn't there. So we're going to have to put a bit more work in to compile this 3-file program. And how do we do that? Well, you may remember from that lesson in compilation that a preliminary step before you get an executable is an object file. So we're going to, and this has absolutely nothing to do with objects in object-oriented programming, although I guess there's a rough correspondence between us making implementation files for different types, which then goes into that type's object files. But don't think about object-oriented programming. Please don't. So we need to use that -C flag to just make an object file, no executable, and use that to make an object file for our data types implementation. And note that we have some stuff in a different order than we're used to. Typically, we would have -O and the output file name at the end. Now it's in the beginning. That's fine. It doesn't matter. The order of these arguments is kind of arbitrary, and I think it looks a bit nicer with -O at the end, because you could think of it as reading left to right, the output being the last thing after the input. But really, it doesn't matter. So anyway, we're going to compile our string implementation into a string object file, and then use the string object file to finish compiling main.c. So let's do this. Oh wait, forgot the -C. Cool, so now we have string.o. Recall that string.o is a binary file, so it's useless to open it up in a typical text editor. This has the code that makes up the string implementation. Oops. Oh, I'm still in the shell. Also, don't worry about size of example. This just came up in a discussion with a specific student about use of size of, and isn't part of this example. So now that we have string.o, we can compile main.c. Okay. I was still a bit suspicious of this. Okay, so in this last part of the lesson, I'm going to go a bit ahead in order to let this string example finish compiling. The thing I was worried about was this line. We define a string variable, but we just talked a whole bunch about how we don't want users of our code, as in people writing code that builds on ours, to be able to know the implementation of types. But yeah, this just plops a string variable into our program. So I think it's finally time to talk about dynamic memory allocation. I'm going to talk about it in more detail in a later lecture, but yeah, let's just use the last little bit to use it to patch up our program. So for starters, instead of using a string variable, we're going to use a string pointer. And then we're going to modify makeString to return a pointer to a string rather than the struct itself. And why are we doing this? It'll become clear later. Just trust me, bros. We're changing the function signature of the makeString function to return a pointer. Using that pointer thing again. And then we talked a lot about how returning like pointers that are on the stack, so pointers to other stack memory, is dangerous because that memory will be, oh, sorry, question?
Yeah, sorry, this is kind of a bit ancient, but up to what lecture does the test cover?
That will depend on how far I get, but most likely tomorrow's lecture.
Tomorrow. Okay, thank you.
Yeah, I'm just thinking about that. I'm pretty sure Wednesday's lecture is just a review, like talking about what's going to be on the test. And that'll include up to the previous lecture. So yeah, up to tomorrow.
Thank you.
No problem. So where was I? Oh yeah, returning stack memory is bad. But we can return heap memory, no problem. I'll draw a picture to demonstrate. Is this going to end up blinding someone in the audience? Cool. So as seen previously, our functions work on a call stack. So say main has a stack frame and makeString has a stack frame. Ooh, I should have made this wider. Good thing I'm using a pencil. And within each stack frame, is a bunch of local variables. The details don't really matter. And we have saw previously that returning an array on the stack is very problematic because the array is being stored right here. And then when make string is popped off the stack and some other function's stack frame is popped onto the stack. Is this readable? Like, no. Yeah. Hold on, I'm going to take a few moments to fiddle with lights. That's more like it. Cool. So what was I saying? Returning a stack-based array is bad because it might get overwritten, or it almost certainly will get overwritten as more functions are called. Since arrays are basically just pointers, the same idea applies to pointers. Returning a pointer to stack memory is very bad because it'll just point elsewhere in the stack, and that memory will get overwritten. But recall our memory model. With a code section, a big ol' heap, and a stack section. We're going to define a local variable that is a pointer that doesn't just point elsewhere in the stack. It points to a memory location in the heap. This is super useful because heap memory will last beyond the end of the function that it's defined from. So, I shouldn't say defined. It'll outlast the stack memory of the function where the pointer to it is defined. To sleep. There we go. So I think I'm going to basically leave you all on a cliffhanger, elaborate on how dynamic memory allocation works in the next lecture. And yeah, that'll be the cutoff for the test. Just as a quick overview, I guess, you use a function called malloc. You pass into it the number of bytes you want to allocate, so the size of your type, and it returns a pointer to that many bytes. You don't need to know about how your operating system manages heap memory in order to use it. You just give it how much space you want, and it gives you a pointer to that much space allocated specially for you. So yeah, we'll talk about malloc tomorrow, but until then, have a good day.